The last thing we want to do in chapter 11 with polynomials is we want to work with basic operations with polynomials. One thing we've already done this a little bit already is identifying like terms. Remember, like terms, they have to have the exact same variable with the corresponding exponents. It has nothing to do with the coefficients of the terms. So if you look at 3a squared b and negative 2/3 a squared b, notice how the variable part a squared b, those both have the same variable part with the corresponding exponents. So that would be an example of what we call like terms. If I have negative 8xy squared and 7x squared y, notice how we have the same variables, but the exponents are not corresponding. The negative 8xy squared term has the power of x raised to, the x is raised to the power of 1, but in the 7x squared y, notice how the x is raised to the power of 2. And the y's are also backwards with their exponents. So that would be a no, not a yes. Notice how we have 10a squared, 10ab squared, and notice how here we have negative 2 times ab squared. This really needs to be simplified first. So negative 2 squared would actually be a 4. And remember that power of 2 has got to come through there. That's actually a squared, b squared. So that's how actually these are not like terms. So that'd also be no for C. So that's how I have x to the fourth y cubed and then negative 2y to the third x to the fourth. Remember, multiplication order can change. So I can change this second one to negative 2x to the fourth y cubed, because typically we want our letters to go in alphabetical order. So we do have same variables with the same corresponding exponents. So that would be a yes. Notice how we do have the same variable, but they're not raised to the same exponents. So again, that would be no, they're not like terms. So the catch is when we have like terms, this is going to help us what we call simplify or what we call combine like terms. So we're going to look at examples of combining like terms. So also we're going to see this word simplify. The instructions to simplify the expression are vague, but often are used in mathematical exercises. In general, to simplify an expression means to write the expression using fewest terms or reduce or lower coefficients or exponents. In other words, write it with the fewest things possible. It's like when you text. A lot of times we want to try text with fewest words possible. Simplifying kind of means the same thing. So we want to keep that in mind as we move forward. So simplifying algebraic expressions by combining like terms. So combining like terms, again, I can show this on paper, but you can also kind of mentally do this as well. So notice how we have this 5x cubed plus this 2x cubed. When we do that, what we're picking up on is, do we have like terms? So notice how they both have x cubed. So if they are like terms, what that means is you have 5x cubes plus 2 more x cubes, which means we have 7x cubes. So if you have like terms, what we do, as you recall, is just simply add the coefficients. That's going to be just 7x cubed. So if I have negative x to the fifth plus negative 4x or minus 4x to the fifth. So again, we have x to the fifth minus 4x to the fifth. Notice how, again, if I use the circle method, we do have these two terms. And they are like terms because they both have x to the fifth. And the catch is adding the coefficients. Remember, the coefficient of x to the fifth is actually 1. So what you're really doing is going 1 plus negative 4. Because remember, when I use the circle method, this becomes an addition problem, 1 plus negative 4. So 1 plus negative 4 becomes then this negative 3x to the fifth. So C, notice how we do have a lot of terms, but notice how the a to the third and the 3 to the third are like terms. So we want to put those together. So it's going to be 4a to the third. And notice how we would have then this positive 4a squared and this negative 6a squared. Notice how those are also like terms. So I can also combine those together. So this becomes then 4 plus negative 6, which is going to be a negative 2 or minus 2a squared. We usually don't write it with the plus negative 2 because it's too many symbols. So that's understood to be 4a squared plus negative 2a squared. They just write a subtraction because, again, they mean the same thing. So look at D. Again, we have the 5m does have a like term with it, which is the negative m, or negative 1m. So we do have like terms there. 3 and a negative 1 is going to make a 2. So it's going to be 2m plus then this 5n. And we can't go any further because 2m and 5n are not like terms. So they're not addable. And then e, we have, there's this y and there's this y. Nothing else is like terms. So if I'm going to put it in kind of an order, the y cubed would come down first. The negative 5y squared would come down second. And a y becomes then a 2y. That would be about as simple as I could take that problem and combine like terms. Subtraction gets a little tricky for some folks. There's a little statement here, but I'll just kind of model the way I like to do it as well. So if I want to subtract, notice how you have to subtract this whole quantity. It's in parentheses. So when the whole quantity is in parentheses, what we have to actually do is we have to focus on the subtraction part first. So in doing this problem here, this a, we're going to write down the y squared plus the 2y, but we're going to actually, you either consider like multiplying a negative 1 through, or just simply distribute the negative through and change the signs. So either way, what's inside the parentheses must change signs. So 3y squared turns into a negative 3y squared, and that positive 5y has turned into a negative 5y. So to drop the parentheses, the subtraction sign on the outside has to be dealt with first by bringing it through, either by multiplying by negative 1 or just simply changing the signs of each term. So once we do that, we now notice that this y squared and this negative 3y squared are like terms. So we want to add its coefficients. So 1 plus negative 3 would be then this negative 2y squared. And then our attention turns into, we have this 2y and this negative 5y. So those are also like terms. So 2y and negative 5y becomes then a negative 3y. So that would be our simplification of that. So on B, notice how the first polynomial, and then we're subtracting the second polynomial. But the first one, the parentheses are just saying we have this 4-term polynomial, but since there's nothing outside the parentheses, those parentheses can drop. M cubed minus this 3m squared minus this 5m plus the 4. But notice how we have subtraction present. With subtraction present, on the second polynomial, all the signs inside the parentheses must drop, or change, I should say, before when we drop the parentheses. So that 4m cubed turns into a negative 4m cubed. This negative 2m squared turns into a positive 2m squared. Notice how this is getting kind of long. So what I'm going to do here is actually drop it underneath. So the negative 4m cubed is what I'm going to have next. So that's going to go underneath the m cubed. Then we have this negative 2m squared is going to turn into a positive 2m squared. And then this negative 5m is going to turn into a positive 5m. And this 2 is going to turn into negative 2. A lot of times it's easier to add vertically than horizontally. So now I have a 1 and a negative 4, which is going to give me a negative 3m to the third. And negative 3 plus a 2, that's going to be a minus 1m squared, or just minus m squared. Notice that 5m, negative 5m and 5m will zero out. So that term just drops out altogether. And 4 and a negative 2 just gives me a positive 2. So that problem turns into that. So next thing we'll get into is multiplying polynomials. So multiplying polynomials can be a little tricky because it involves sometimes the distributive property. So we'll see where this takes us here. So again, we've already kind of done a little bit of this already. So to multiply a monomial times a monomial, we're kind of familiar with that. We're just going to kind of do the same thing we've been doing. But here they're going to make them a little bit more complicated with positive and negative numbers. So if I look at 4x cubed times 4x times 3x squared, notice how we want to multiply the coefficients together first. So if you multiply the coefficients together, 4 times 3 is going to give me a 12. And then x times x squared, we would follow the rules of exponents, which means we actually add those exponents, and that'll be x to the third power. Notice how if I have negative 6y squared times 2y cubed, again, we want to multiply those coefficients together to start with. Negative 6 times 2 would be a negative 12. And then y squared times y cubed, we would add exponents, and that would be y to the fifth. So negative 12y to the fifth. And remember, that's really like a negative 1 times a negative 3. That's actually going to be a positive 3. And a times a would be a squared. So that's how we kind of multiply the monomials. So if factors are to be multiplied times a factor with more than one term, we have to apply the distributive property. So remember, factors are connected by multiplication. So here, the 2x would be considered a factor. And since the x squared minus square x is in parentheses, that all becomes a factor. Now, to perform multiplication, what we must do is we must distribute the 2x through the parentheses. So each term must be multiplied by the 2x. So it's kind of what we just did up here, just got to do 2 times. So 2x times x squared becomes then just 2x cubed. So 2x times negative 4x, so we multiply the coefficients. 2 times negative 4 would be negative 8, and x times x would be then x squared, and that would be our answer to that. So if I have this negative 2y, I gotta multiply that through all 3 pieces. So to distribute this, we got to do this 3 times. So again, we'll multiply the coefficients together. Negative 2 times 2 would be a negative 4. Y cubed times y squared becomes y to the fifth. And then we got to multiply the coefficients together. Negative 2 times 5 is negative 10. And y cubed times y would be y to the fourth. So negative 10 y to the fourth. Then we got to multiply negative 2 times negative 6, which is a positive 12. And the y to the third would just come down. So again, if we do this problem, distribute properly, got to multiply this 4a through all 3 things inside the parentheses. So 4a times 3a cubed, we have to multiply the 4 times the 3, which is 12. A times a cubed would be a to the fourth. 4a times negative 2a squared would be 4 times negative 2, which is negative 8. A times a squared would be a to the third. 4 times, and that's actually a negative 1, if you will. 4 times negative 1 is going to be a negative 4. And a times a would be a squared. And we would have that as our expanded form of that using multiplication with respect to the distributive property. So applying a binomial times a binomial can be complicated. So sometimes what we can do is use what's called the box method or the area model. Because remember, area actually means to multiply. So if you bear with me, like for instance, if I gave you, say, 21 times, say, 13, you know, we learned to do this as 3 times 1, which is 3. 3 times 2 is 6, 0. 1 times 1 is 1. 1 times 2 is 2. And then we'd add all that together, those 2 partial products, and add them together to get our total product, which would be 273. What we can do, remember in a rectangle, to find the area of a rectangle, that's length times width, 13 times 21. So the answer to this inside here has to be 273. Now, an interesting thing we can do, though, as an organizer, is I can partition this 13 into a 10 and a 3 using place value, because the 1 means 1, 10, or 10, and 3 ones. So I can partition it one way this way. And a 21 kind of means 20 and a 1. So instead of thinking if it's a 21, I can think of it as a 20 and a 1. And then we can kind of use distributive property kind of concept here, find the area of each individual box. 10 times 10 is going to be 200. 10 times 1 is 10. And then we do the 3 through there each time. 3 times 20 would be 60. And 3 times 1 would be 3. And notice how, you know, I would probably add the 10s together. So I would have, you know, 200 plus 70 plus 3, 200 plus 70 plus 3. In other words, that would be 273. That's the way we can kind of do this. So what we would like to do on this problem right here is there's 2 ways of doing it. One way is what's called the box method. So x plus 4 would be one edge, and the x plus 2 would be the other edge. So essentially what this becomes is an organizer. So then we just kind of apply what we just did a second ago. We just multiply through the parentheses, or now we just multiply x times x is going to be x squared. X times 2 is going to be 2x. And then we bring the 4 through. 4 times x is 4x. And 4 times 2 would be 8. So we end up with that as our answer. And notice how, again, the diagonal actually are like terms. So our answer becomes then this x squared plus this 6x plus this 8. So that would be another way to do it. So if I want to multiply 3x minus 5 times the quantity of 2x squared minus x minus 1, a good organizer is actually a box. So I'll just make it big enough to make things go inside there. So I have a 3x and a negative 5. That's my two terms. I have a 2x, a negative x, and a negative 1. So if I bring this through here, 3x times 6x, I'm sorry, 3x times 2x becomes 6x squared. 3x times the negative 1x, that would be like negative 3x squared. I'm sorry, what did we write down here wrong? I wrote something down wrong, didn't I? Yeah, that should be 2x squared there, shouldn't it? So let's back up here. Yeah. Something a little suspicious. Let's try it again. 3x times 2x squared would actually be 6x cubed. Do that different color. Color here. So that would be 6x cubed. And then 3x times negative x would actually be negative 3x squared. And then 3x times negative 1 would just be negative 3x. Negative 5 times 2x squared would be 10x squared. 10x squared. Negative 5 times negative x, so that's like a positive 5x. And negative 5 times negative 1 would become a positive 5. And notice how typically, the diagonals will are like terms. So it's a good organizer to kind of do this. So that would be then the 6x cubed does not have anybody to go with. The negative 3x squared and the 10x squared would be a positive 7x squared. And then the negative 3x and the 5x would be a positive 2x. And then the 5 would come along for a ride. So if I want to do 2x squared plus 3x minus 2 times 3x squared minus 5x plus 6, same kind of concept, just make a bigger box. So I'm going to have like 3 partitions. Got 3 terms in each one. It doesn't have to be perfect. You can kind of see that's pretty sloppy, but still, it should do the trick. So we have a 2x squared, the 3x, and negative 2 becomes one edge. This 3x squared, this negative 5x, and the 6 becomes the other edge. So we just do 2x squared times 3x squared, which would be 6x to the 4th. 2x squared times negative 5x would be negative 10x to the 3rd. 2x squared times 6 would be 12x squared. 3x times 3x squared, just kind of do the same process over again. 9x to the 3rd. 3x times negative 5x would be negative 15x squared. 3x times 6 would be 18x. Negative 2 times 3x squared would be negative 6x squared. Negative 2 times negative 5x would be 10x. And then negative 2 times 6 would be a negative 12. So again, we typically have those diagonals are like terms. Those all look like they're like terms. This is working. I just loaded one, just kind of giving it a glance. So we have then 6x to the 4th, and that looks like a negative 10 plus a 9 would be a negative x cubed. Then we have a 12, and a negative 15 would be a negative 3. A negative 3 and a negative 6 would be a negative 9, negative 9x squared. 18 plus 10 would be 28x. And then the negative 12 would drop one in on the end. That kind of helps you do your math in an organized manner. So they're also modeling some ways to do it in that, doing it that way. We also have what's called the FOIL method. So in multiplying 2x minus 1 times x plus 3, you may recall it as FOIL, where F stands for first, I stands for inner, I'm sorry, foil, can't even spell it, can I? F-O-I-L. Try that again. F-O-I-L, outer, inner, and last. So another way to do this is using what's called FOIL. So the 2 and the x are considered the first terms of each binomial, so they're called the first terms, so they get multiplied together. And then the outer terms are the 2x and the 1. So that's my first two moves, would be that. And then my next two moves would be here to here, that's the inner terms. And then the outer terms would be the -3 and the 1, if you can see some patterns there with that. So notice how there's still going to be these four multiplications. So you have to do 2x times x, which would be 2x squared. And then 2x times 1 would be a positive 2x. And then you do -3 times x would be -3x. And do -3 times 1, which is -3. And then typically, your two middle terms usually are going to be alike a lot of times. So we end up with then the 2x squared, and then that's going to be a -x minus 3. That would be considered what we call FOIL to do it. Now, FOIL only works if you have a binomial times a binomial. It doesn't work if you have a binomial times a trinomial or a trinomial times a trinomial. It only works for a two-termed by two-termed. So keep that in mind. We also get into what we call special products. So if we have x plus 3 times x minus 3, notice if we use FOIL on this, we get x squared minus 3x plus 3x minus 9. But notice how the middle terms actually zero out, and all we're left with is the first terms and the last terms. So this is an interesting one that actually becomes really easy to work out, in that sense. So a lot of times when we see this a plus b times a minus b, we call this a sum and difference of the same two terms, or conjugate pairs. So a lot of times their product is called the difference of two perfect squares, is usually what when I see this, I usually call it the difference of squares. But notice how we have this a plus b and this a minus b. And we use that word conjugate, if we recall, with working with imaginary numbers. So they have that a plus b, a minus b concept. So if we have the same factors, but one's a plus and one's a minus, this actually becomes really easy to do. We can actually describe it as a formula, a squared minus b squared, to do it, if you will. So if I have this a plus 2 times a minus 2, notice how these are what we call conjugates each other. Or in other words, one factor pair has a plus and one factor pair has a minus there. So notice how if you got in that situation, all you really got to do is square the first term. X times x is x squared. And remember, it's always going to be a difference of squares, so it's going to be a minus. And then all you got to do is square the 2. 2 times 2 would be 4. X squared minus 4 becomes the answer. So that's how we have this 2a plus y, 2a minus y. So notice how we have the same factors, but just one's a plus and one's a minus. So the quick way is remember that this is just a difference of two squares. So I got to square the 2a. So 2a times 2a is 4a squared. And then y times y is y squared. Or in other words, we have a minus y squared. Some people treat it as just FL. Don't worry about the FOIL, just do the F and the L. So the other way of doing it is just say 2a times 2a and negative y times, or positive y times negative y. That's because remember the outer and inner are just going to drop out anyway. So this is more like FL. That's the other way to do it. So it's either way, it can be done rather quickly. It's a kind of a shortcut one. The other one we pick up on is if you have x plus 3 times x plus 3, this is described as x plus 3 squared. So these are interchangeable. So this is what we call a square of a binomial. Remember, binomial means 2. So if we have a binomial squared, notice how we can kind of work this out as, let's do this with a cleaner marker, x plus 2 times x plus 2. Again, if I want to do this by using FOIL, the first terms are the x to the x, and then the x goes with the 2, that's the outer. And then you loop it in. The 2 goes with the x, that's the inner. And then the 2 goes with the 2. Those are my four multiplications. So x times x is going to be x squared. X times 2 is going to be 2x. 2 times x is going to be 2x, and 2 times 2 is going to be 4. Notice how we have two 2's there in the middle, or two 2x's, I should say. So we have that kind of double. Notice how it's x squared plus actually two 2x's plus 4. In other words, we have x squared plus 4x plus 4, if you will. So if I look at 2x minus 5 squared, notice how we can write this as 2x minus 5 times 2x minus 5. And I can use FOIL to actually multiply this out, or the box method, if you will. The box method also comes in handy. So if I do the FOIL, that's 2x times 2x and 2x times -5. But then we got to come back through here and go the -5 times the 2x, and then the -5 times the -5. That's our multiplication. So if we do that, we have 2x times 2x, which is 4x squared. Then we have the outside's going to give me a -10x. The inside's going to give me a -10x. And the last term is the -5 times -5 is going to give me a positive 25. So notice how there's a 4x squared. Notice how there's two, those 10x's there, -10x's, if you will, plus this 25. So notice how there's two of those guys in there. So in other words, we have 4x squared minus this 20x plus this 25. So it becomes that. So we're starting to materialize some patterns there that we start to discover. So 3a minus 2b squared, that's the same thing as 3a minus 2b times 3a minus 2b. So again, if I want to use FOIL to do this, 3 times 3a, 3 times the 2b, and then we have the inside -2a, -2b times 3a, and then -2b times -2b. That's our four multiplications. So we would have then 9a squared, and then that'd be a minus 6ab, and that'd be another minus 6ab, and then we'd have a positive 4b squared. So notice how, again, there's two of these in the middle. That's doubled. So notice how we really just have 9a squared and two -6's, or in other words, a -12ab plus this 4b squared is what we're starting to pick up on. So what we pick up on is there's actually going to be this pattern. So to square a binomial, what you do is you square the first term of the binomial, and then you multiply the first term and the second term of the binomial together, and then double it. That'll give you your middle term. And then all you got to do is square the third term, or square the second term to get the third term of the trinomial. So notice how when you square a binomial, you're going to end up with a trinomial. So notice how if we have x plus 2 squared, our strategy is just square the x. So x times x is going to be x squared. Our next move is when you multiply the first term into the second term, and then you double it. So 2 times x would be 2x, but if you double it, that's going to be a 4x. And then if you square the last term, 2 times 2 is going to give me the 4. That's going to be my three terms. So x squared plus then this 4x plus this 4 becomes the answer. So if I have 2x minus 3 squared, if I want to do that without using FOIL, our strategy is square the first term. So if you can do 2x times 2x, that's going to be 4x squared. To get the middle term of the trinomial, what you do is multiply the 2x times -3, and you double it. Well, -3 times 2 is 6x. So notice how I can actually go this direction. -3 times the 2, -6x. And then we double it, that would give us a -12x. And then we square the last term, -3 times -3 is going to be a positive 9. So we have that. So our answer becomes then 4x squared minus 12x plus 9 becomes our trinomial. So if you square a binomial, it's actually going to turn into a trinomial. So our last example was 5x plus 1 squared. So again, to do it using the pattern, we square the first term, 5x times 5x is going to be 25x squared. And then to get the middle term, we multiply the 5x times the 1. So 1 times 5x is actually 5x. And then to get the last term, we square the 1. 1 times 1 would be 1. So that's my 3 terms. So if we put it together, 25x squared plus 5x plus 1 becomes our trinomial for that. So we don't actually have to use FOIL or box method. There's a lot of mental strategies to these as well. Okay. So next thing we'll get into is what we call dividing polynomials. So again, we've kind of done this before, simplifying monomials. Remember, that's when we subtract exponents. So that's how the 2 is going to stay put. 4 minus 1 is going to give me this 3, so that's going to be 2x cubed. Notice here, though, we actually have to deal with these fractions a little bit. This -6 over this 2. Notice how I can write that numerator as a -2 times this 3 times a y to the 5th, and the 2 on the bottom is 2y to the 3rd. So notice that I can't make the negative go out. The negative's got to stay the problem. But notice how I can divide the 2's out, and that's going to give me a -3, if you will. And then y to the 5th over y squared, y to the 5th over y cubed is going to give me a y squared. So it becomes -3 y squared. Because notice how the 2's are actually going to divide out, and then I'm allowed to subtract the exponents of the variables to do that. So if you look at this, notice how -4 divided by -4 divided by +4 is actually going to be just a -1. And notice how if you do your x's, there's going to be 1x left on the bottom. So that's going to be -1 over x. Here, notice how you have the 5 and the 15 I can divide out, and I'm going to be left with the 3 on the bottom. If I subtract the x's, though, 4 minus 2, that's going to be 2. So if I put that all together, you can either put the negative out in front or on top. I like to just leave it on top like they did. So I'm going to write this as -x squared over a 3. That's how we usually write it. I usually like to keep the negative on top, but you can also put it out in front as simply the opposite of x squared over 3, like this as well. Notice how, again, the 3 and the 12 can be canceled out, or again, you can use prime factorization. You have 3x, and then 12 is like 2 times 2 times 3 times x cubed. So that's how you can mark out the top. You can cancel out the 3 and the 3, and the x's subtract, leave you 2 x's on the bottom. So the whole numerator falls out. So you have a 1 as a placeholder. You have a 4 left over on the bottom, and you only have 2 x's left on the bottom, since the x's are going to cancel out there and leave you just 2 x's on the bottom. So we've already kind of done that before. What we haven't done is something like this. So 18a to the 4th plus 15a to the 3rd minus 9a squared minus 12a divided by 3a. Now, to divide this, the easiest way to do it is separated into 4 separate division problems. So we can write this as 18a to the 4th over 3a plus then 15a to the 3rd over 3a minus then this 9a squared over 3a, and then minus this 12a over 3a. So all of a sudden, we got to do what we just did a minute ago 4 times. So if you're good with some mental math, this isn't so bad. So that's how the 18 divided by 3 is going to give you 6, and you can subtract the exponents to leave you with 3a's. So it's going to be 6a cubed. 15 divided by 3 is going to be 5. And then if you subtract the a's, it's going to leave me 2a's. So it's going to be a plus 5a squared. Notice that 9 divided by 3 is going to be 3. Subtract your a's, it's going to leave me an a. So it's going to be minus 3a. Here, 12 divided by 3 is going to be 4. And the a's will divide out. This is going to be a minus 4. So that's how that problem will look like. So if I look at part B, so notice how, again, I can separate this as 3 separate fractions. So I can write this as 3x cubed over x cubed minus x squared over x to the 3rd. A minute ago, we didn't want to separate, but here, when we separated, it actually made a problem without fractions. So it actually was advantageous for us to do it. This one doesn't look as pretty. If we do it, we do have this x thirds divide out. That gives me a 3. Let me get that back in another color there. It's getting too much. Okay. So that's how the x thirds would cancel out. That's going to give me a 3. And then 2 minus 3 is going to give me a 1 on the bottom. So minus 1 over x to the 3rd. I'm sorry, just 1x left over. should say. So that one there, it almost looks better off written like it was. So that's what we see there. So the next one we have is, again, if we separate it, it's going to be 2x or 6x cubed over 2x squared plus then 2x squared over 2x squared. So again, we can just divide out. 6 divided by 2 is going to be a 3. And there's 3 x's on the top and 2 on the bottom, so you can remove 2 of them and you're left with 1 on the top. So that's 3x. So take some thinking there. And notice how everything here is the same on the top and bottom, so that all divides out. Remember, we use 1 in division to represent when it all divides out. Now, here we have to divide by a binomial. To do this, we use what's called long division. So if we call a long division, like if I do, say, 3 into, say like 126, you know, the way we do this is we go 3 goes into, you know, well, we would say 3 goes into 12 4 times. 4 times 3 is 12. When we subtract, get a remainder of 0. The 6 slides down. 3 goes into 6 twice, so we'd say 42. Now, another way to do this is say 3 goes into 100 plus 20 plus 6. You know, so how many 3's can I get into 100? In other words, if I cover up that 0, I could say, well, how many 3's can I get into 10? Looks like 3. So it looks like 30 would be a good answer. So I'd say 30 goes here. And 30 times 3 would be, so we have, let's see here. So 30 times 3 is going to be actually a 90. And if we subtract that, we get a remainder of 10. What you want to do is bring that 10 over and add it to the next spot. 20 plus 10 gives me 30. So then we can go 3 into 30. 3 into 30 would be, 10 times. So 3 times 10 is 30. We get a subtraction and a remainder 0, so we can bring the 0 over to the 6. 6 plus 0 gives me 6, and 3 goes in 6 twice. So 30 plus 10 plus 2 gives me then 42. That's long division, where it kind of looks more like a polynomial. So notice how there's this, we kind of start at the top here to start with. So to do x minus 4 is what our divisor is, and we want to divide into 2x cubed minus 9x squared plus 7x minus 12. And always make sure your polynomial is counting down 3, 2, 1, 0. If it's not, we need to use zeros as some placeholders in our math. So to do this, what we do is ask ourselves, what times x is 2x cubed? What times x is 2x cubed? Well, I need a 2x squared is what I need. So what we do is we put the 2x squared up here. That's got to match the first term. So then what I do is I multiply 2x squared times x, and I multiply the 2x squared times -4. That has to multiply through both pieces. So this becomes then a 2x to the third minus then 8x squared. Now the catch is, in algebra, when we subtract, we actually add the opposite. So what we did is we come in here and just change both signs and actually add. So then we just do this all over again. Once we add, that's going to just leave me what, a negative x squared. So what I ask now is, I'm up here at this spot, what times x gives me negative x squared? What times x gives me negative? So now we're down here now. What times x gives me negative x squared? So that's going to have to be a negative x. So then I multiply the negative x times x and get negative x squared. And negative x times -4 would be -4x. So remember, in subtraction, we actually add the opposites. So this negative actually changes to a positive, and this negative turns to positive, and now we actually add. So the negative x squared and the positive x squared are going to zero out. So I have to remember there's a 7x plus this 4x gives me 11x. and then the negative 12. I'm going to just bring this all down so I don't forget about it. So now I'm at this spot here above the 7x, but I'm looking at this down here at the 11x. So what times x gives me 11x? Well, what I need there is going to be a positive 11. So 11 times x is going to be 11x. 11 times negative 4 is going to be negative 44. So then again, remember when we subtract, we actually, in algebra, add the opposites. So I change the signs and actually add. So we do that math. So that gives me then this negative 12 and a 44. That's going to be actually a remainder of, what is that, 32. So in algebra, we can actually do that, negative 12 plus 44, because now we know about positive and negative numbers. So since this remainder is smaller than the degree of this over here, you know, this is a degree 1, this is a degree 0. So once this falls below the degree 1, we can no longer do any math. So this becomes a remainder. So sometimes the remainder is written as a, 32 over x minus 4, or sometimes they just call it remainder 32. So see if we can do another one of these here. So I have x cubed plus 1 as my divisor, and we're going to divide that into 2x cubed minus 9x squared plus 7x minus 12. So to do this, what we got to watch out for is this didn't count down very smoothly. So let's see what we got going on here. So our first move, of course, though, is we're above the 2x cubed. What can multiply by x cubed to get 2x cubed is our first move. So we pick up on that. That's going to be a 2. So 2 times x cubed is going to be 2x cubed, and 2 times 1 is going to be a positive 2. So what we have then is we have to subtract, so we just change the signs. So this is going to come out, and this is going to be a negative as well. So then we add, and that's going to be a negative 9x squared plus the 7x, and that's going to be a minus 14. But notice how this is a degree 2, and this is a degree 3. So since our degree is smaller, since this is x squared smaller than degree 3, this becomes our remainder. So this becomes then plus then, since it's minus, so I actually put a minus sign there. We'll put a minus that. And then this becomes our 9x squared plus the 7x minus 14 over then the x cubed plus 1 becomes our division. So we don't get a whole lot to gain out of that. If I divide by x minus 1, let's see if I can do that. So if we do this one the other way, so x minus 1 this time is going to go into 2x cubed minus 9x squared plus 7x minus 12. If we do this division, so again, we have to focus on what can multiply by x to give me 2x cubed. So we're kind of in this first position here. So that should be what, 2x squared. So 2x squared goes up here. And 2x squared times x is going to be 2x to the third. 2x squared times negative 1 is negative 2x squared. So then we come through here and we're going to change the signs. So this is going to become a negative and this is going to become a positive. And now we go back to adding these integers or these terms. So we end up with the first pair drops out, but negative 9x squared and 2x squared becomes then negative 7x squared. The plus 7x comes down and the minus 12 comes down. So then we move into the next position. What times x gives me negative 7x squared? That's our question. So we're going to need a negative 7x. So it's going to give me a negative 7x squared plus 7x. So again, if we change our signs, this becomes a positive, this becomes a negative. So everything drops out except the negative 12. So now the degree is too small. So what we end up with then is a remainder. So we put like minus then this 12 over this x minus 1 becomes our answer to that. So that's a little bit about long division as well. I don't know how much the book does on that, but it kind of takes you through that. So hopefully you find that helpful for today.